In this video, I'm going to explain you about some example of a vector space. So first question what we are going to do here is let us show that R is a vector space over R. In general, for any field F, it is always a vector space over F. Okay, for any field F, that it is always a vector space over itself. So I'm defining two operation because a vector space should be defined according in two operation. One is plus and one is scalar multiplication. So I'm defining the plus as I take the set R cross R goes to R defined as plus AB. It is defined as A plus B for all AB belongs to real numbers. And the scalar multiplication, I'm taking the field also as real number. So real number cross real number, we get to real number. Okay. And so the scalars here I'm taking as alpha, and the vector here I'm taking as a from the real numbers, but both are real numbers, so alpha into a will be also a real number. So we are defining in this way. So first of all, we have to prove that it is an abelian group. So first of all, let us prove that R is an abelian group under addition. So here R is not empty, we know, because 0 belongs to R, and we can now try to show it is a binary operation. So if you take two real numbers, then a plus b also belongs to real, because sum of two real numbers is always a real number. So that what this shows that plus is a binary operation. Okay, so this show it is nothing but plus is a binary operation, and we know that addition of real number is always associative. So addition of real number is associative. Suppose e is the identity element, then this property should be satisfied under addition. So from here we can easily find what is e we got as 0, which belongs to real number for all a belongs to real. So e equal to 0 is the identity element or the additive identity. Now suppose if I take b be the inverse of a, then a star b should be equal to identity, which is equal to b star b plus a. So a plus b is equal to identity, we got 0, so 0 equal to b plus a. So this implies what is b? We can find that b is nothing but minus a. Okay, b is nothing but minus a. And this, if a belongs to real number, then minus a also will belongs to real number. So we got the inverse. So every element has an inverse. Okay, under addition every element has the inverse. Now we'll try to show it is commutative, or so I take two real numbers such that a plus b means if you add two real numbers and if you commute, it is always commutative. Okay, addition of two real number is always commutative. So here we have shown that R plus is an abelian group. Okay, so now we are going to prove the fourth condition of a vector space under scalar multiplication. Using the scalar multiplication, we are going to apply this, and we try to show that this fourth condition also holds. Okay, so the first condition here is this alpha a plus b. Now alpha is also a real number, a plus b is also a real number, so I can multiply this alpha inside, so we get alpha a plus alpha b. So this is also a real number, this is also a real number, so the sum of two real numbers is again a real number, so this will belongs to real numbers. So this condition is true, as well as if I take two scalars, means two scalars, these are also real numbers, so sum out, so here also we have a real number, so we can multiply this inside, so we get alpha a plus beta a. So this alpha a is a real number, because alpha is a real number, a is a real number, so product of two real number is a real number, so this belongs to real number, as well as beta is a real number and a is also a real number, so product of two real number is again a real number, so sum of two real number is a real number, so this belongs to real numbers. In the same way, this also will be true, as well as 1 into a. So 1 into a is always a for all a belongs to real numbers. So all the four conditions of a vector space are satisfied. So hence R is a vector space of R. Okay, so in general, if F is a field, then F is a vector space over F. Now I will try to show that R squared is a vector space over R. So I'm taking R squared. So I'm defining two operations. One is addition and scalar multiplication. So R squared cross R squared, I have to go to R squared. Define as, I will take any one element from here. So the element of this will be coordinate wise, two coordinates, two tuples. So x1, y1, and here also the elements will be tuples. So that is x2, y2. So this is sent to where? x1 plus x2 comma y1 plus y2. So it is sent to this x1 plus x2 comma y1 plus y2. We are adding coordinate wise here, and the scalar multiplication are taking one scalar from the real numbers, and the element from here I'm taking as x1 y1. How I'll multiply each coordinate with this. So alpha x1 comma alpha y1, this also belongs to real numbers. Why it belongs to real numbers, real R2? Because this belongs to real number, this belongs to real numbers, so the whole thing will belongs to R2. Now we'll try to show, first of all, it is a group under addition. It is an abelian group. So first condition is it is non-empty. It is clearly non-empty as 0, 0 belongs to R2. Now let us check it is binary or not. So if I take x1, y1 belongs to R2 and I take x2, y2 belongs to R2, let us add these two elements. So we have to add coordinate wise. So we have x1 plus x2, y1 plus y2. So this is a real number. This is also a real number. So sum of two real number is always a real number. So this part belongs to real number. Okay, this one belongs to real number, as well as this also. Y1 is a real number, y2 is a real number. So if you add two real number, you will again get a real number. So this belongs to real number, this belongs to real number, so the whole thing will belongs to R2. So that's why the plus is a binary operation. Let us check it is associative or not. So I'm taking three elements in R2 with this condition. Now we'll add coordinate wise. For this we use the first operation, addition. So we add coordinate wise, so we get x1 plus x2 comma y1 plus y2, and we'll add with this. So if we get x1 plus x2 plus x3, y1 plus y2 plus y3. Now these are real numbers. Okay, so we know addition under real number is always associative. Addition of real number is associative. So here we can apply associative law of real numbers. Okay, we are not interchanging directly the bracket, means we are applying the associative law of addition for real numbers. Since all are real numbers, so we can apply the associative law of addition for real numbers. Here also we can apply the associative law of addition for real numbers. So if you apply the associative law of addition for real numbers, the bracket, we can interchange the bracket, so we get this because of associative law. And here also, so this can be separated as x1 y1, and here we get x2 y2, x2 plus x3 comma y2 plus y3. That is nothing but x2 y2 plus x3 y3. So it satisfies the associative law. So plus is associative. Now suppose I take identity element to be this, then I take one element in R2. So I'm taking an element in R2 as x1 y1 plus e1 e2 equal to x1 y1. So if I bring this one this side, I can find that e1 e2 is nothing but 0, 0. So your additive identity element is nothing but 0, 0 is the identity element. And in the same way, let us take the inverse. Suppose this is the inverse of this, then this plus this, I should get 0. That is the identity element. So from here I can easily find this, so this will go this side. So I get minus x1 minus y1, which belongs to R2. So that's every element has an inverse in R2 under addition, means every element has an inverse. Now let us check the commutative or the abelian part. So we have x1 y1 and x2 y2 belongs to R2. You add these two. Okay, x1 y1 plus x2 y2 is equal to what? X1 plus x2 comma y1 plus y2. Now addition, these are real numbers. Okay, so these are real numbers. So addition of two real numbers is always commutative, so we can interchange this. So we get here x2 plus x1 comma y2 plus y1. So here also is a real number. Okay, so this can be, this can be separated as x2 y2 plus x1 y1. So we got here x1 y1 plus x2 y2 is equal to x2 y2 plus x1 y1. So this shows that R2 plus is an abelian group under addition. Now we'll try to prove the fourth condition of the vector space. Okay, try to prove the fourth condition of the vector space. So I'm taking here this one, alpha here, alpha x1 y1 plus x2 y2. So here we'll add. Okay, so we are going to add this one. So x1 plus x2 comma y1 plus y2, adding coordinate wise. Now using the second definition, okay, so using the second definition, I'll multiply to each coordinates. Okay, so alpha x1 plus x2, alpha y1 plus y2. Now you can multiply throughout. So alpha x1 plus alpha x2, alpha y1 plus alpha y2. So this can be written as alpha x1 comma alpha y1 plus alpha x2 plus alpha y2. So from here I can take alpha common, and from here also I can take alpha common. So we have proved this. Now here this we are taking two scalars alpha plus beta. Using the second definition, I can multiply to each coordinate, so we get alpha plus beta x1, alpha plus beta y1. So x1 I can multiply to each, so alpha x1 plus beta x1, alpha y1 plus beta y1. So alpha x1 comma alpha y1 plus beta x1 plus comma beta y1. So from here I can take alpha common, from here I can take beta common, so I get this is equal to this. And in the same way for the scalars, so we can apply the definition too. So if we multiply to each coordinate, so we get alpha beta x1, alpha beta y1. So here we have C. Okay, so this is a real number, this is a real number, as well as x1 is a real number. In the same way, this is a real number, this is a real number, and y1 is also a real number. So multiplication of real number is associative. Okay, we know that multiplication of real number is associative. Using that condition, we can interchange the bracket. So we have interchanged the bracket here. We get alpha beta x1 comma alpha beta y1. So alpha you can take common, so we get beta x1 comma beta y1. Then you can take beta common, so beta x1 y1. Okay, so here using the second definition of what we have, the second definition, you multiply 1 to each coordinate. So 1 into x1, 1 into y1. 1 into x1 is nothing but x1, 1 into y1 is nothing but y1. So we have proved all the four conditions of a vector space, and this R2 satisfy all the four conditions of a vector space, as well as it is an abelian group under addition. So it is nothing but it is a vector space over R. Hence R2 is a vector space over R. So this is your homework. So do in the similar manner as I have done. So you have to prove R3 is a vector space of R with the definition this. So I'm defining addition in this way. So I'm adding coordinate wise, and the multiplication I am defining as scalar multiplication. You multiply each coordinate with the scalars. Okay, so for all x1, y1 and x2, y2, z2 belongs to R3, and the scalar alpha belongs to real number. Thank you.